Hi, my name is Tom Hoeffel, and this channel is designed to help students learn chemistry. In this video, we're going to be talking about periodic table trends, more specifically, atom size, ionization energy, and electron affinity. We're going to use these Bohr models to kind of help describe these periodic table trends. And basically what a periodic table trend is, when we're talking about atom size on a periodic table, does it increase going up or down on the periodic table, or left or to the right? And we're going to use these Bohr models to explain the why they do that, as well as their trend itself. So let's jump right into it. The reason I picked these Bohr models to represent is that sodium and chlorine are in the third row on the periodic table. So when we're talking about left and right movement, we're going to pick two atoms that are in the same row. For up and down on the periodic table, I picked sodium and potassium. And if you look right here, sodium and potassium are right next to each other up and down on the periodic table. So if we're talking about up and down movement on the periodic table, we're going to compare these two atoms. But if we're talking about movement left and right on the periodic table, we use the sodium that's on the left-hand side of the periodic table and the chlorine that's on the right-hand side of the periodic table. And at the end of the day, all this is going to come down to two reasons, okay, or what I call justifications. If you're taking the AP test, their popular phrase is justify your answer, okay? In college, it might just be explain your answer. And in high school, the same thing. What is your reasoning, okay? But when it comes to periodic table trends, there's really only two explanations or justifications of why the things are acting the way they are. And we really want to hammer both of these justifications, okay? So let's go right into atom size, okay? And when you look at these two atoms, when we're going up and down the periodic table, I think this is actually pretty easy. I think it's pretty easy to decide that the potassium is actually going to be larger than the sodium. Okay, now remember, we have to have a justification as to why. And if you look at the two, this one has 3 rings and this one has 4 rings. So really it comes down, the more rings you have, the bigger the atom's going to be. Because the atom is actually, the size of it is going to be based on the atomic radius, which is the distance from the nucleus to the outermost ring. Okay, if you have more rings, that atomic radius increases, and obviously the size increases. So for our justification of going up and down the periodic table, it's simply going to be the number of rings. Now, there's a lot of words that can be substituted for rings. So let's go ahead and write that down first, though. So it's going to be the number of rings. They also could be called shells, electron shells, electron clouds, or energy levels. There's a lot of words actually that can be used to describe, these rings. These orbits is another word. Energy levels, electron clouds, shells. It all means the same thing. Okay, so going up and down the periodic table, okay, it's all about the number of rings, and that's not just going to be true for atom size. It's also going to be true for ionization energy, of which we'll get to in a moment, as well as electron affinity. So this justification, super, super, super important, okay? Now, let's go left and right. And when we're going left and right, we want to compare two things that are in the same row. Sodium's in the third row, and chlorine's in the third row. Sodium's on the left-hand side of the periodic table, chlorine's on the right-hand side of the periodic table. And if I asked you the question, which one of these atoms is bigger, how would you answer? Okay, well, let's do some investigation on the atomic structure. The sodium has 11 protons and 12 neutrons, and it has these 3 electron rings. If we look at chlorine, it has 17 protons and 18 neutrons, and it still has these 3 rings, although on the outermost ring, there are more electrons, okay? So those are the major differences between the two. So which one's bigger and which one's smaller? To be honest with you, for a new student, I think this is a very difficult question, okay? And I think there's a concept that you need to learn, okay? And that concept for going left and right on the periodic table It's all about effective nuclear charge. So let's go ahead and write that down. Effective nuclear charge. And effective nuclear charge has an equation where it's Z sub EFF, which is equal to Z minus S, where the Z stands for nuclear charge and the S stands for screening electrons. And I'm going to explain both of those right now. Okay. So the first part, nuclear charge. What does that sound like? Well, the word nuclear kind of sounds like the nucleus, and it is. Okay. So it really is, what's the charge of each of the nuclei up here? So let's take a look at the first one, and I'll do the first one. Hopefully you guys can do the other two. So the nuclear charge of the nucleus, well, if the nucleus consists of 11 protons and 12 neutrons, well, to be quite honest with you, I could care less than how many neutrons there are. There could be 1,000,000 neutrons. It doesn't matter because neutrons have no charge, okay? The only thing that has charge in the nucleus is going to be the protons, and they're each worth 1 plus, okay? So if I have 11 of them, the nuclear charge in a sodium atom is 11 plus, okay? Why don't you guys go and try to do the other two, okay? If we're looking at chlorine, 17 plus, and who cares about the neutrons? This is going to be a 17 plus. And as far as the potassium's nuclear charge, 19 protons, that's going to give me a 19 plus, okay? So nuclear charge, super, super easy, okay? Screening electrons, okay? This is going to be the number of electrons from the nucleus to whatever you want to talk about. And if we're talking about atom size, we want to talk about the valence electrons. So we want to know how many electrons are in between the nucleus and my outermost region, okay? And it looks like the first ring and the second ring added together. In this one, it looks like there's 10 screening electrons. And effective nuclear charge is just the nuclear charge minus the screening electrons. So 11 minus 10 tells me that the effective nuclear charge is 1 plus. Now, what that means is that this nucleus has an effect on this outermost electron of a 1 plus, okay, which is not very strong at all, okay? Let's see what potassium has, okay? So once again, the screening electrons are the electrons between the nucleus and our valence electrons, which are the outermost region of the electron. So for something that has 4 rings, okay, the screening electrons are going to be the first 3 rings because that's what's screening our valence shell, okay? So it's going to be 2, 8, and 8, which is a total of 18 electrons. And if you subtract the 2, you're going to find out that the effective nuclear charge of a potassium is also +1, okay? Why is that? They're in the same column on the periodic table. Everything in the same column is going to have approximately the same effective nuclear charge. And there's a lot of different formulas that you can use. This is kind of like a basic one. So for all intents and purposes for what we're doing, it is going to be the same. Okay, so everything in column 1 is going to have a 1 plus as far as its effective nuclear charge. Let's take a look at something that's on the right-hand side of the periodic table. Okay, remember our nucleus is a 17 plus. Okay, but the only electrons that are screening the valence electrons are these first 2 shells. Okay, and 2 plus 8 is going to give me 10 screening electrons. 17 minus 10 gives me an effective nuclear charge of 7 plus. So this nucleus does a much better job of attracting that last ring, okay? It kind of has a charge of 7 plus, okay? And it's so much better than the 1 plus. So this nucleus, okay, is going to be able to pull that third ring in tighter than something with an effective nuclear charge of +1. It's going to try, but it's not going to be able to really pull those rings in at all, okay? So sodium is going to be the bigger atom because of a weak effective nuclear charge. Or you could say that chlorine is going to be the smaller atom because it has a higher effective nuclear charge. Either way, when you're moving left and right, excuse me, left or right on the periodic table, it's all about effective nuclear charge. Okay, so to sum things up here, as far as atom size gets bigger as we go down the periodic table because the number of rings are increasing, okay? And the size of the atom gets bigger as we move left on the periodic table because the effective nuclear charge is weaker, okay? So I'm going to come over here next to atom size, and I'm going to write down AS, and I'm going to talk about how those things increase, okay? So it's going to increase to the left because of a weaker effective nuclear charge, and the atom size is going to increase going down the periodic table because the number of rings is actually increasing, okay? And we're going to use these same justifications to talk about ionization energy and electron affinity, okay? So let's go ahead and jump into the next periodic table trend, which is going to be ionization energy. Ionization energy is the amount of energy required to remove an electron. In other words, it's kind of like how well does the atom hold on to its electron. So if this marker was an electron, and I'm just kind of like dangling it out like here, I'm going to have a low ionization energy because it's not going to take a lot of energy to remove the electron if I am only holding on to it like this. Versus if I'm holding it down with a death grip, okay, holding really tightly onto that electron, it's going to take a lot of energy to wrestle this electron away from me if I'm holding on to it for dear life, okay? So some of these elements up here are holding on to their electron better than others, okay? Let's go ahead and compare sodium and chlorine. Which one of these elements do you think is actually holding on tightly to its electron versus very loosely, okay? Well, remember, left and right has everything to do with this idea of effective nuclear charge. And the chlorine has a +7, so it's the one with the death grip, okay? Where the sodium is the +1, where it's just kind of like dangling the electron out there. So we will say this has a very low ionization energy. It does not take a lot of energy to remove an electron from something that has an effective nuclear charge of +1. Whereas over here with the chlorine, it's going to take a lot of energy. So this has a high ionization energy because of its effective nuclear charge of being +7. So over here, I'm going to go ahead and write down IE, which stands for ionization energy, and it increases to the right because of an increase in effective nuclear charge. Okay. Now let's talk about going up and down. Okay. Which of these, holds on to their electron better? If we look at the effective nuclear charge, they're both +1. Okay. They're both kind of holding on to it fairly loosely, but one is actually holding on to it a little bit better than the other. But remember, when we go up and down, it's not about effective nuclear charge. It's going to be about the number of rings. Okay. So is something with 3 rings able to hold on to their electron better than something with 4 rings? Okay, that's pretty much the question that we're asking. Now, a little demonstration here. I have a magnet, okay, and my board's magnetic, okay, so it takes a decent amount of energy to pull this electron off of this magnetic board, okay. But what happens if I put some pieces of paper in between, okay? Now, these pieces of paper are supposed to be representing electron shields or electron rings, okay? And if I have some pieces of paper there, okay, it might be a little bit easier to pull the electron off versus when there was no electron shields. And if I increase, if I bring in some more pieces of paper, it gets even, you can see it. I mean, the magnet's barely, wow, that magnet's barely holding on, okay? And it's really easy to pluck it off with all of these electron shields, okay? So the more shielding you have, the more rings you have, which potassium has more rings, okay? It's easier to pluck off the electron, okay? Now remember what ionization energy is. the amount of energy required to remove an electron. And if we're talking about which atom it's the hardest, or which one has the highest ionization energy, it's going to be the sodium because it doesn't have as many rings. So once again, I'm going to come over here and I'm going to talk about how the ionization energy increases going up and down. It increases going up the periodic table because when there's less shields, okay, like for example, no shields here, it's harder to pull off the electron, okay, because of the attraction to the nucleus, okay. So up and down is always about the number of the shields. The more shields you have, okay, the easier it is to pull off the electron. If you have a low number of shields, the harder it is to pull off the electron, and that means a higher ionization energy. The last one we need to talk about is electron affinity. Electron affinity is the amount of energy released, okay, when an electron is added to an atom, okay? So if I had an electron here and I was to give it to one of these two, okay, one of them will release more energy, okay, based on that addition of the electron. So it's kind of like which one likes it more, but I don't like to use the word likes because these elements don't have feelings, okay? There's going to be scientific principle that explains why that is. So if I had an electron right in the middle, okay, which of these two would, be more likely to release some energy to become more stable, okay, when the electron is added to the atom, okay? And if we're talking about sodium and chlorine, once again, it's going to come down to effective nuclear charge, because effective nuclear charge is the reason why things act the way they do, going left and right on the periodic table. And something with an effective nuclear charge of +7 not only holds onto its electrons really well, but it also does a good job of kind of attracting those electrons so it can release some energy, okay? And remember, when we release energy, you get to a lower energy level, okay, and that actually increases the stability. That's a theme that we have here in chemistry. So going left to right, the electron affinity is going to increase due to a higher effective nuclear charge, okay? Now, there is one exception, okay? When you get all the way over to the noble gases already has this shell filled. For example, if we were one more space over from chlorine to argon, argon would have 8 valence electrons here. So even though argon holds onto its electrons really, really well because it has a higher effective nuclear charge, it's not going to take anything else in, because then they would have to add a whole nother ring, and that would not make it more stable, it would make it less stable. So our exception is going to be that electron affinity increases going to the right until you get to the noble gases. So down here, I'm going to say except the noble gases, which I'm going to abbreviate with NG, except the noble gases. All right, how about up and down with electron affinity, okay? When we put an electron here, okay, which one's going to release more energy, okay, based by the addition of the electron? Well, it really comes down to which one can kind of take it in more easily. And it's going to be, again, the one that has less shields. If there's no shields, the electron's going to be easily attracted to the nucleus, okay? If we added all those pieces of paper in there, the attraction would not be as strong. So as we go up the periodic table, okay, electron affinity increases due to a lack of shielding, okay? So that kind of explains the three periodic table trends, the three major periodic table trends. Sometimes you can throw electronegativity in there as well. It's going to act exactly the same way as electron affinity. Electronegativity is the ability to attract electrons, and then you'll end up finding that there's some correlations that if I have a high ionization energy, meaning I'm holding on to the electron really well, I also do a good job of bringing in other electrons. That's what electronegativity is, okay? Whereas if I have a loose grip on my electrons, low ionization energy, I'm probably not doing a good job of bringing in other electrons. And then the last thing I want to cover is some equation writing for ionization energy and electron affinity. So let me erase this portion right here. And let's talk about ionization energy again as far as writing an equation for it. This is called the first ionization. And I'm going to do the first ionization for the element magnesium. Now, remember, ionization energy is the amount of energy required to remove an electron. So what we're trying to do here is take away electrons. Now, the way we do that, you might say, hey, can we just subtract an electron? And that's going to create a change. And when you subtract an electron from something, it's going to make it positively charged. And I'd say, yeah, that kind of makes sense, except one thing, okay? We don't write minus signs or subtraction signs in chemistry equations, okay? So if we were to do just a little bit of math, okay, we would add an electron to both sides of the equation. This would cancel out, and the equation would then be magnesium is going to go under a change. It's going to make a magnesium ion, and I'm going to have an electron over here. So when the electrons are on the right-hand side of the equation, it really is the subtraction of electrons. And I'm going to use my marker as an example. The magnesium over here with the cap, okay, and the cap's going to represent an electron, okay. So the magnesium's neutral over here, okay. Then a change occurs. We're going to take off the cap. We're subtracting the electron, and you're going to have the electron and now something that's charged because this just lost an electron, okay? And if you lose an electron, you'll end up being positively charged, or what we call a cation in chemistry. Now, this is just the first ionization, and magnesium typically does not lose one electron, it typically loses two. So I'm going to write the second ionization for magnesium, okay? Well, if you're doing the second ionization of magnesium, that means an electron has already been removed, so you have the magnesium positive ion. It's undergoing a change. It's going to make the magnesium positive 2 ion because the second electron is going to come off. So here's the first electron that came off in the first ionization, and this is the second electron that would come off in the second ionization. And that would result in a magnesium positive 2 ion if 2 electrons were removed from the magnesium. So we just got to get comfortable with writing these equations for the ionization process of magnesium. This is the first ionization, and this is the second ionization. And so that's a little bit of equation writing for ionization energy. We also have equation writing for electron affinity. So let's go ahead and do electron affinity. Now, electron affinity isn't about removing electrons. Electron affinity is about gaining electrons, okay? Because remember, it's the amount of energy released when an electron is added to an atom, okay? So I'm going to do the first electron affinity, and I'm going to pick the element sulfur, okay? So sulfur, if we are going to add an electron, okay, it's okay for us to use plus signs, okay? We just can't use subtraction signs. And when the sulfur has an electron that's added to it, it's going to make a sulfur -1 ion. So in this case, we're creating negative ions because we're gaining electrons. In the last example with ionization energy, we created positive ions because we were removing electrons. And we would call this the first electron affinity because an electron has been added to sulfur 1 time. If we talk about the second electron affinity, we are going to take the result here, which is sulfur that's -1 that has already had an electron added to it, and we're going to add the second electron. And when we add a second electron to something that already has one that's added, you'll make a sulfur that's -2, okay? So when the electrons are on the left-hand side, we're adding electrons, and when the electrons were on the right-hand side in our last examples, we were actually subtracting them. So once again, electron affinity is all about creating negative ions by gaining electrons, where the ionization energy was the exact opposite. We created positive ions by subtracting the electrons, and those electrons were on the right-hand side. So we just got to get comfortable with writing these different types of equations. And if you just want to see the comparison, when we did the I1 and the I2 for magnesium, just to get this practice in again, it was magnesium changing into magnesium ions where an electron was subtracted. And if I repeated that one more time, it would look like this. So when the electrons are over here, we're adding them and creating negative ions, and we call that electron affinity. When the electrons are on the right-hand side, that really means subtraction, and we end up creating positive ions, and we call that ionization energy. So hopefully all this helped. We used Bohr models to talk about the periodic trends of atom size, ionization energy, and electron affinity, and we were able to explain why through these two justifications, and the real lesson is right here, talking about going up and down the periodic table, where it's the number of rings, or going left and right, having everything to do with this concept that we call effective nuclear charge. And if you feel like you learned a lot in this lesson on periodic table trends, please hit like and subscribe so that the algorithm works out to where this information is pushed to more students that want to learn chemistry.